Hello and welcome to Radio Propagation Mapping. This presentation was originally recorded for the BayCon 2022 virtual conference for the BayNet Amateur Radio Club. My name is Marcel Stieber, Alpha India 6 Mike Sierra. I was first licensed in 2008 as KI6QDJ while I was a student at Cal Poly San Luis Obispo, where I received my master's degree in electrical engineering with a focus on RF and communications. I was heavily involved with the Amateur Radio Club at the university, and I still serve as industry advisor to the club today. I'm also involved with Cupertino Aries as a repeater trustee, and involved with the Salinas Valley Repeater Group and several other groups as a volunteer RF consultant and tower climber. The slides and video for this and my other presentations, you can find them at my QRZ page, and you can also reach out to me via Twitter or on my YouTube channel for other presentations. So today we're going to be talking about the basics of radio propagation mapping. We'll be focusing on the higher frequencies, so VHF, UHF, and up. And we'll also cover some of the common programs that we use for this that I like to use. So one is Radio Mobile Online by VE2DBE, and the other is Ubiquiti's free airLink and ISP design software available online. We'll do a couple demo use cases for each of these as well to kind of show you what these programs can do and how it might help you in your next project. So first off, radio propagation mapping. Typically, we do this to get some visual representation for radio coverage. So if you've seen maps like this one on the right here, that's typically what you'll see. Repeater owners like this, clubs like this, because they can put it on their websites to show the coverage that their repeaters have. So that's quite useful. It could also be used for other things like infrastructure planning. So propagation mapping is used to figure out where to put cell phone towers or where to put TV transmitters or radio transmitters for commercial as well. You might use it for event radio coverage. So if you're doing event support and you're setting up a temporary radio, or you're trying to figure out maybe where your simplex communication coverage starts and ends for different nodes or different rest stops, that can be useful. You can also use like Ubiquiti software for more network topology development. So if you're building a larger internet service provider, wireless internet service provider, or you're building up an AREDN or a HAM-WAN mesh system, you might want to put all the nodes down and kind of develop your network topology. You can also use it for coverage studies, which is kind of similar to just repeater coverage maps as well. You can do point-to-point links to understand which links you can make, what's line of sight, what's not, if different frequencies or power levels will work. And you can use this for interference analysis as well, using a similar kind of point-to-point analysis between, say, two different repeaters in different parts that may or may not be causing interference for each other. So that's quite useful. When we look at the basics of radio propagation, it's always really interesting to look at the history. So the fundamental algorithm that's typically used is known as the Longley-Rice Model, also known as the irregular terrain model. And this was first developed by Anita Longley and Phil Rice in 1968 by what is now known as the Institute for Telecommunications Sciences. So this algorithm that developed, it's open source and downloadable. You can literally go to the .gov website and download the source code and then build your own software or play around with this. I just love these little pieces of history, like this memo from 1985. This was a little bit after they had released the original algorithm. Someone found that had some, inconsistent results in certain use cases, corner cases. So they made a tweak to the algorithm and published a new version of the algorithm. So they now have a version 1.2.2, which was released in 1984, so several years later. So the basics of this Longley-Rice model, or irregular terrain model, is that it takes a bunch of inputs and it gives you a reference attenuation output. So the types of inputs it's providing are things like the distance between the transmitter and receiver, the antenna heights of each of those, the types of antennas, their gain, the frequency you're operating at is very critical. And then there are these kind of geographic things like terrain irregularity, surface reflectivity, and the Earth's effective curvature, right? So as these, it's not just a flat map, you have to account for the Earth's curvature. Different types of surfaces between those two nodes can make a difference. So if it's trees, if it's rocky or sandy surface, or if it's a lake or an ocean, those all behave differently and will cause different reflections and different propagation. So when the algorithm takes all these inputs, it then gives you a reference attenuation output. It's literally a single value that it gives out. And this lets you calculate the path loss. So if we go to really basic path loss calculation, this would be your receive power is your transmit power, adding any gains like antenna gains or amplifiers, and removing any losses like your reference attenuation or other signal or cable losses. So if we do a really simplified version of this and just do a really simplified example, if we take a 10 watt radio transmitter, that would be 40 dBm, and we take a reference attenuation that the algorithm gave us of 100 dB of loss, then we simply plug that in with 40 dBm of transmit power, with no gains in this case, and 100 dB of losses, which gives us a received power of minus 80 dBm, or about 22 microvolts. Given that a typical radio is somewhere in the half a microvolt range of sensitivity for receive sensitivity, this would be a strong signal, and you'd be able to make this link. So this is a very basic idea to give you an idea of how these calculations work. So if we extrapolate this over to one of the pieces of software, so this is Radio Mobile, and if we take Radio Mobile and now do just a simple link, we can do a link here between, in this case, we'll do the two repeaters in the Bay Area, so W6TDM, that's the Cupertino repeater, and W6HP. And if we just do a link between these two using the default values here at 146 megahertz, so 2 meters at 20 watts, this is a nice simple example that we'll just use and plug in to see what it gives us. So the results here are just for a single point-to-point study, right? So this is just a link study, like that simple path loss example. You can see the W6TDM repeater here in the valley floor and the HP repeater up on the ridge line. So the link between these two, they'll give you the elevation of the two, they'll give you the free space loss and all the calculations that go into this. And then the result here is that we have a 10-kilometer link at 2 meters where we put 40 watts in, and the received signal strength at the HP repeater was 92 or 91.5 dBm, right, or about 6 microvolts. So this is, again, a relatively strong signal coming into that receiver, and they can definitely hear this just fine. They've got about 22 dB of fade margin. So this is a very basic radio link study. In this image as well, you can see the Fresnel zone. They have the Fresnel zone in here for the spreading and coming back to between the transmit and receiver, and this just gives a nice visual representation. You can also see different ridges, so if you selected a site that was not line of sight, or you had these hills a little bit higher and they intruded into the Fresnel zone, you could see how that impacted the actual performance of the system, so the reference attenuation would change in that case. So you can see if we extrapolate this now, we're going to go one step further, and I'll show you a little bit here in Radio Mobile how you can actually do this. So we'd go in and create a new site is the first thing. This case, we're going to go down to Fremont Peak near Salinas. So this is one of the Salinas Valley Repeater Group sites. So here at Fremont Peak, we can just drop and place the cursor at center. We'll put it here roughly at that site. You can also change this to satellite view if you prefer to have like satellite imagery and allow that to load. It's usually easier just to keep it pretty simple. So if we submit that, that would allow you to save that. You can name the site whatever you like, but then you can take that as an input now for your actual mapping. So if we go to a new coverage study, I've selected that Fremont Peak site. We're just going to leave all the defaults here just to kind of show you what the software will put out. So here again, all your different inputs. So 2 meter antenna height. It's an omnidirectional antenna with no tilt to it. And 6 dBi of gain, so just kind of a normal base station kind of antenna. The typical receive station will be, again, a 2 meter high mobile antenna with only 2 dBi of gain, so kind of more just a dipole. And we'll do this one at 2 meters with the default of 20 watts, and these default kind of line loss settings. You can see, though, if you're setting up an actual repeater system, you can put in the actual values that your system would be using, so the specific antenna, the actual height that you have, and any losses or feed line. If you have 200 feet of half-inch heliax, you could calculate that and put it in here, as well as specific transmit loss and such. In this case, they're using a half a microvolt for their receive sensitivity threshold, which is a pretty good value, and I usually just leave the defaults here as well. The other things that are kind of useful is playing with the range. So the larger the range, the larger your block sizes will be, because they kind of do a calculation, and the rendering here makes the difference. So the rendering determines the block size based on the size of that range. So in this case, I'm just going to choose 100 kilometers and do the low resolution mapping just so you can do that quickly. If you're using the online one, that's running on their servers, so you might have to wait quite a bit longer if it's a higher resolution one. If you download the software on your computer, then it's just limited by your computer's processing power. So if we look at the results for this one, this is what the 20 watt Fremont Peak repeater coverage looks like at up to 100 kilometers range. So you can see, in theory, they're saying that you can get coverage all the way up to the South Bay. In a couple spots, there are a couple splotchy spots here, so maybe you start losing it. As this color goes from green to yellow to nothing, that's where the signal gets weaker, right? Now, you have to keep in mind this is not accounting for any buildings. Those aren't in here. It's just using basic surface reflectivity and pieces like that. So if you do account for buildings, if you're in an HT at one of these locations versus if you're a mobile or a base station, obviously that's going to have a big impact on your signal capabilities. So the other thing I'd like to point out while we're on this software is this is a little bit optimistic, if you will say. So I've often found that plotting with the default values is a little bit optimistic for actual radio performance, especially if you're dealing with, like, I'm often doing event support and kind of calculating where to put repeaters for a temporary deployment. So typically you have handheld radio users that might not have high gain antennas. They're less trained operators, or they're not setting up a big base station. So often what I'll do is I'll drop that power number significantly. So if we drop this down to 1 watt here, I put this plot, you can see this is a little bit more pessimistic. So it got a little bit less green. The coverage here into the South Bay area you can see is almost all yellow, which is, I think, a little bit more accurate for this repeater. And it just brings in and gives you a little bit more pessimistic results. I find this is actually really useful to do when you're doing plotting, because you can kind of turn up and down these knobs and adjust how that performs. So that's the short version there for radio mobile. And we'll switch back to kind of talk about the software, and then give you a couple other demos as well. So Radio Mobile is a software, the one I just showed you. It's free, both available online with Radio Mobile Online, which is graciously provided by them, or the Windows download version. So you can download the software and run it on your computer. Then you run it. I mean, you could put it on a server at home if you wanted, if you have a powerful machine, and run those calculations, or you can just let them run. Usually they don't take too long. The online one only takes a couple minutes usually, I've found. If you're doing a really high resolution one, it might take longer. Really depends on the settings you're using. The great things about Radio Mobile, it's incredibly powerful and configurable. So really you can set all sorts of things. It really gives you really detailed access to each of those factors in the Longley-Rice algorithm. So you can go in and tweak those to your heart's desire. You can play around with it as much as you want. And it's really powerful. It also has a really broad frequency coverage range, so you can do anything from 20 megahertz to 20 gigahertz in the ham bands, so they make it free for amateur radio frequency operation. They also accept donations on their website. Of course, encourage people to do that if you're using their software. And you can do link calculations like we showed you, or propagation studies to do some mapping. Downsides of the software, there's definitely a learning curve, especially with all these parameters. That's why I kind of recommend just start playing around with it. Pick a repeater that you know or that you're comfortable with, and just kind of play with it and see how those settings adjust and how that responds to your real world experiences with that machine, to kind of understand that, right? I also mentioned that the results are often optimistic, so kind of tweaking those inputs to make it figure out. The software also does take longer to generate the results, so it's not instant, right? You do have to wait a little bit. I had these preloaded for the demonstration today, but if you're running those calculations and it needs to actually go through and do a high resolution map or remap something, you're waiting for that each cycle. So that's just one of the things to keep in mind for that software. So with that in mind, let me introduce Ubiquiti software. So Ubiquiti is a manufacturer that builds all sorts of wireless devices. A lot of people might know their access points and their Unify system, pretty common for kind of prosumer home Wi-Fi systems. And a lot of commercial systems and wireless internet service providers, or WISPs, will also use these systems. So they have two pieces of software. airLink is their existing software. ISP Design Center is the new one they just released last year in 2021 in alpha. So it's still very new and is still getting a lot of kinks worked out of it, but it's pretty powerful, and they're likely going to switch to that fully, I'm assuming. So just keep that in mind as you're learning these pieces of software and playing with it. So both of these are free. They're available online. You do have to make a free account with Ubiquiti to be able to really play with it and save things. But it's really fast. So the nice thing is it's real time. You can plot things in real time and see these things in real time as well, which is really cool. The great thing is you can also generate shareable links. So you can generate a link and share it to other people that you're collaborating with, and they can view that same network that you've built and the coverage that you've shown to do that. So that's really useful. The downsides to this software, it's really only designed for higher frequencies, so 900 megahertz and up. Ubiquiti doesn't even sell their 900 megahertz equipment anymore, but they still support it in their tools. So that's the lowest frequency you can select. And you're much more limited with what control you have over the tool. You can't select all the individual parameters for the algorithm. You're kind of choosing one of their pieces of equipment, because of course they're trying to sell you their equipment, and using that to then create your models. So for someone like an AREDN system or the San Francisco Wireless Emergency Mesh or Bay Area Mesh Group, as they're called, the SFWEM and BAM group, they're using this very heavily to kind of do modeling and propagation studies as well. So keep that in mind. I'll show you a couple little hacks that can work, and I really like to do this. So we'll switch over here to the Link UI page. So this is Ubiquiti's airLink system. And you kind of start on a base page. Again, we're going to do this Fremont Peak repeater just as kind of a demo to show that. You can see how they load it all here. You would click on add a new point to multi-point. So I'm going to show you the hack now. This is my trick for how to make repeater coverage quickly and easily. So place that main unit where you want it. You can delete these client nodes. So these are client nodes. So we don't need either of those. So those can both go away. We're going to select the device here to be the 900 megahertz device. So that's as low as the frequency goes. So if we're going to be modeling a VHF or UHF repeater, we want to get as close to that as possible. By selecting this Rocket M900 device, we can then select a custom antenna. So right now you can see this has a sector antenna on it. It's a 90-degree sector antenna. And that's not really giving us the good propagation that we want. So if we click here on custom make this antenna a 360-degree omnidirectional antenna, you can see where we're going with this, right? So you can adjust the range here. So we can increase this range out further, and we can go almost all the way and make it, again, you know, that 100 kilometers, so the same range that we had for the other map. So we'll go just shy of 100 kilometers here. And now you see we already have an original plot here. So this plot is, again, going to be even more pessimistic than that 1 watt VHF plot we did in Radio Mobile. You can see here in the South Bay area, there's almost no coverage according to this, because again, at 900 megahertz, you're not going to have as much propagation out that far. It's not going to knife edge, there's less refraction, and there's more path loss as well. So a couple things that you can do to tweak this even further, right? So right now we changed the antenna, so we made it omnidirectional. If you're only looking in one direction, you could change that around. You could increase the gain of this antenna as well. So this lets you go up to 50 dBi of gain. So we can do that. But you see that doesn't really change much here on the map. So the one that I really like to tweak is the height. So if you move this height significantly higher, so we move this up to, I don't know, 30 meters now, we'll say. At 30 meters, we'll already start seeing some improvements. But heck, this is crazy. Let's go 400 meters height. So if we go to 400 meters height, you can see how this starts filling in. So this lower Salinas King City Valley filled in almost all the way to King City. Right? If we go back down to 12 meters, which was the default starting point, then you can see initially this is all cut off, right? So this is all gone. If we go back, and that was not even, this is at 12 meters. There you go. All of this is gone, right? Nothing in Greenfield, nothing in Soledad. If we go up to that 400 meters again, this is completely unrealistic, but we're kind of hacking the software to get an idea of what sort of coverage we might get. This is more like what your VHF coverage is going to look like, right? If we go back to that map that we had, this was the 1 watt VHF plot. You can see this coverage down here almost all the way into King City. So if we compare this VHF plot to this 900 megahertz plot, but the antenna is at 400 meters above the ground, they're actually quite similar, right? So this is my fun little hack for how to get kind of the similar idea. Now, knowing, of course, there are a lot of asterisks on this, but for real-time mapping and doing quick adjustments, this is pretty neat, right? And if we want to move this repeater, hey, let's go down the ridge with this repeater, you can literally pick this up, drop it over there, and that quickly you have the new results, right? You can see it's got shading over here because that larger peak is there. So this is what's really impressive about this software, and it's just super fast to use. And if you're okay kind of with the hacks that might be there, that's just one thing to keep in mind. So we'll briefly switch over and do a demo here on their newer ISP Design Center. So this is their software that is the newer version, and it's really designed for internet service providers, right? It's in the title. In this case, I'm mapping out the microwave link that exists between the Black Mountain repeater, so the WW6BAY repeater, and the East Bay site for the BayNet Amateur Radio Club. So when we look at these, I've already pre-plotted the actual sites. Unfortunately, this software doesn't support 3 gigahertz, which is what this link is actually at. So we kind of have to make a choice here. We can either go down to 2.4 and choose one of their devices, or we can do 5 gigahertz, which will be a little bit more pessimistic than an actual 3 gig system, right? So, oh, and my internet's a little bit slow. There we go. So at 5 gigahertz, with just these standard antennas from their air fiber system, they claim we can get a link of 219 megabits per second, which would be pretty slick. It's a long link. It's 62 kilometers long, so you definitely have quite a bit of path loss playing in here at these higher frequencies. If we want to kind of compare, at a lower frequency band, so if we wanted to drop this, say, down to their 900 megahertz band, we could just go with 2 nanostation locos, for example, and you can see at this lower frequency, you have only 5 megabits of throughput with this system, right? So it's pretty neat. You can tweak all these things, right? You can adjust power levels again. You can change channel width based on how you have this set up, but it's really designed for their equipment. This is great for people using AREDN and doing similar things like that, because you can really plot out your system and map that out very nicely. Okay, and the next thing I'm going to do here is, some of you might know that recently the BayNet Amateur Radio Club added an AREDN node here, so they added an AREDN sector at this site. So what we can do is we can actually add that as an access point to the site, and this is pretty neat. So again, we'll have to kind of hack this a little bit because the equipment's a little bit different that we're using, but at 5 gigahertz, we actually deployed a rocket, M5 rocket there. So we can click M5 rocket, and we can adjust the antenna as well to a 120 degree sector antenna, which is actually the antenna that's up there. And we can adjust the heading and that sort of thing on the antenna as well, or we can manually move it here on the system. So I'm going to kind of roughly adjust it here to where it's pointed, and you can see what sort of coverage you would get here, right? So let me minimize a few of these things. But this is roughly the coverage that you get. Note the color scheme here is a little bit different from their older software. So red is actually the strongest and green and blue are the weakest, which is a little bit counterintuitive, but that's how they're doing their coverage mapping here. So we can see that the 5 gigahertz coverage here out to nodes, and if you want to move these nodes to specific people's homes, you can see whether or not they would have coverage at those sites. And you can see how as you get further out, it starts dropping off as soon as you hit these ridge lines. Of course, there's no coverage beyond that, but the coverage down here in the South Bay would be great as long as there are no trees in the way. And that's usually the biggest challenge that you have. Very good. All right. Well, I think that just about wraps us up here. So just to overview on what we have. So from the mapping tools, the ones that I demoed today, we have Radio Mobile Online from Roger, VE2DVE in Canada, Ubiquiti's airLink, so that's their existing legacy software that I actually really like and gives you a little bit different controls, but for amateur radio, it's actually great for doing that repeater mapping. And then the Ubiquiti ISP Design Center. So this is their newer software. It's really designed for internet service providers, alpha released last year, but super powerful. We're actually using this to start designing some AREDN networks and just get them all in the system. Even if you're using slightly different equipment, you can put all the pieces there and it gives you a really nice network visual to be able to share with people and use for registration and stuff. So a quick summary, Radio Mobile, free, airLink free. The frequency coverage is one of the big differences, right? So you can't go down to those lower frequencies, but they're both available online. You can also download Radio Mobile and you have those links to share. So that just about wraps it up. available for Q&A, and you can always reach out to me at ai6ms@arrl.net or find me at my QRZ or on Twitter or on YouTube. Big thanks to George, John, Rod, and Vince for helping put on the conference this year, and I look forward to any Q&A. Thanks.